Imagine a jet engine pushing its limits. At 1400 degrees Celsius, most high-performance steels don't just weaken, they behave like warm butter, losing the strength needed to hold a plane in the sky. But in February 2026, researchers at USC revealed something that defies the traditional rules of metallurgy. A new alloy that doesn't just survive these temperatures, it thrives in them. This is a high-entropy alloy, or HEA. Unlike traditional alloys that use one base metal with tiny additions, this is a chaotic, equal parts cocktail of tungsten, rhenium, and osmium. In a standard metal, atoms are neatly arranged like a stack of oranges. When you apply heat and pressure, these layers slide past each other easily, leading to material failure. But the W42 Re30 OS28 alloy uses what engineers call the cocktail effect. Because tungsten, rhenium, and osmium atoms are slightly different sizes, they create a distorted, jagged lattice that's impossible to slide. This atomic-level friction is the secret sauce. It creates a massive internal resistance that keeps the metal rigid even when the thermal energy is trying to shake it apart. The result is a yield strength of 1.4 gigapascals at 1400 degrees Celsius. To put that in perspective, that's like balancing a fully loaded semi-truck on a single postage stamp without it flinching. Most aerospace materials would have turned to liquid or deformed beyond recognition long before reaching this point. This alloy maintains its shape where others fail. But how do you even discover a recipe this specific? With 3 elements, there are millions of possible combinations. Finding the perfect ratio is like finding a needle in a haystack the size of a galaxy. The secret lies in the entropy part of the name. By mixing these heavy elements in high concentrations, the system reaches a state of high configurational entropy, which actually stabilizes the solid phase. It's a thermodynamic trick. The universe usually prefers disorder, but here, that very disorder makes the crystal structure more robust against the chaos of extreme heat. This isn't just a new metal, it's a new way of thinking about materials. We're no longer limited by what nature provides, we're engineering chaos to our advantage. This breakthrough at USC marks a turning point for deep space exploration and next-generation power plants. But the way they found it is just as impressive as the metal itself. They didn't find this by accident. They used a process that sounds like science fiction, testing thousands of different metals simultaneously using a specialized 3D printer. To understand how they unlocked this atomic puzzle, we have to look at the machine that made it possible, the digital alchemist. Traditionally, metallurgy was slow. You'd mix a batch of metal, melt it in a furnace, cast it, and then spend weeks testing its properties. If it failed, you'd start from scratch. But the USC team used a technique called combinatorial additive manufacturing. Think of it like a high-speed inkjet printer, but instead of CMYK ink, it uses elemental metal powders. The printer can change the ratio of tungsten to rhenium on the fly, creating a library of thousands of tiny samples on a single plate, each with a slightly different recipe. This isn't just about speed, it's about precision. The machine uses a process called directed energy deposition, where a high-powered laser melts the powders the instant they hit the surface. This allows the engineers to create functionally graded materials. They can print a part that is pure tungsten on one side and slowly transitions into the USC alloy on the other. By testing these thousands of samples at once using automated diamond-tipped probes, they can map out the strength landscape of the entire alloy family in days instead of decades. Imagine trying to find the perfect recipe for a cake, but you have to test every possible amount of flour, sugar, and eggs. This machine bakes 10,000 mini cakes at once and tells you which one tastes best. This rapid-fire approach is how they identified the specific W42 ratio. It was a hidden peek in the data that no human metallurgist would have thought to try manually. But the manufacturing process isn't just about the printer, it's about managing the extreme physical properties of the ingredients themselves, especially the osmium. Osmium is the densest naturally occurring element. It's twice as heavy as lead. Handling it in a 3D printer requires specialized fluid dynamics to ensure the heavy powder doesn't just clog the system. The engineers had to redesign the powder delivery system, using ultrasonic vibrations to keep the osmium particles suspended in the airstream like a metallic mist. This level of engineering is what makes the USC breakthrough possible. It's a marriage of material science, robotics, and high-energy physics. But as we scale up from tiny test samples to full-size engine parts, we hit a massive wall. And that wall is the supply chain of the rarest metal on Earth. Osmium isn't just hard to work with, it's incredibly rare, and in its raw form, it can be unexpectedly dangerous. To understand why this miracle metal isn't in every car and plane yet, we have to look at the dark side of the periodic table. To understand the scarcity of osmium, you have to look at the Earth's crust. For every billion atoms of rock, there is only about 1 atom of osmium. We only produce about 1 ton of osmium per year globally. Compare that to the 2.5 billion tons of iron we produce. It is literally one of the rarest stable elements in existence. This scarcity makes the USC alloy incredibly expensive. It's not a material for your kitchen toaster. It's a material for the most critical components of a multi-billion-dollar spacecraft. But the cost isn't the only hurdle. When osmium is exposed to air, it can form osmium tetroxide, a highly volatile compound that is famously toxic. Even in tiny amounts, this gas can cause severe damage to the eyes and lungs. This is why you can't just melt osmium in an open furnace. The engineering solution? The USC alloy locks the osmium atoms so tightly into the lattice that they can't react with oxygen, effectively neutralizing the risk once the metal is formed. This atomic cage is a masterpiece of safety engineering. It allows us to use the incredible properties of osmium without the deadly side effects of its oxides. But to build a fleet of hypersonic planes or a constellation of deep space probes, we need more than 1 ton a year. We need a new way to source these platinum group metals. Some engineers are already looking towards the stars, specifically M-type asteroids that could contain more osmium than has ever been mined in human history. Whether it comes from the Earth or the stars, the W42Re30OS28 alloy represents a new era. We are moving past the age of found materials and into the age of designed atoms. By mastering the cocktail effect and the chaos of high-entropy lattices, we've created a material that can withstand the most brutal environments in the known universe. It's a reminder that the limits of our technology aren't set by physics, they're set by our ability to rearrange the building blocks of reality. So, the next time you see a rocket streak across the sky or hear about a new world record engine, remember the invisible lattice of W42Re30OS28. It's a tiny, chaotic arrangement of atoms that is quietly making the impossible possible. The heat barrier hasn't just been pushed, it's been broken. Next time you look at a piece of metal, you'll know that deep inside, there's a world of engineering keeping everything together.